11.2 part 2 starts with a couple properties of integrals, and these should look pretty similar. We did these with derivatives. The first I would say is just the constant multiplier. So if you were taking the integral of 2x squared, you could do 2 times the integral of x squared. That would be the same thing. And then the one below is the sum and difference. I really want to make sure you understand that the sum and difference does not work, just like for derivatives, with multiplication or division. We are going to deal with basically one advanced integration technique, which is integration by substitution, and that allows us to take the integral of the multiplication of two functions, given that they're a specific type, which we'll look at in a bit here. So really what the most of this lesson is going to be is making sure that you can access your formula sheet to find those integrals, and then actually applying the integral as we go. Really important to remember that if we don't have an upper or a lower bound, and really you can't only have a lower bound anyway, but if you don't have an upper and a lower bound, then it is an indefinite integral, and you have to include the constant of integration. Now, on your formula sheet, you have been told that the derivative of cotangent is negative cosecant squared. So the integral of cosecant squared is negative cotangent squared. But I would like to use one of the properties here, so I could take this integral and rewrite it as the integral of 6x squared dx plus the integral of the cosecant, oh, I spelled cosecant wrong, genius, integral of cosecant squared x dx. Think of that dx as distributing onto both of those terms. So now I can deal with these, piece by piece. The integral of 6x squared is 6 over 3 x cubed plus a constant, plus the integral of cosecant squared is negative cotangent x plus a constant. Now, when I apply that positive to both, nothing particularly interesting happens, but 6 divided by 3 is 2, so 2x cubed minus cotangent x, and then what I would have is a constant plus a constant. Well, we don't know what that constant is yet. We would have to be given initial conditions in order to find it. So you don't have to write, C1 and C2. You just have to recognize that a constant plus a constant is another constant. So we don't write it twice, we just write it once. And I really do want to re-emphasize this concept that if we are unsure that we've done this correctly, we could check by saying that 6x squared plus cosecant squared x is equal to the derivative with respect to x of what we just found, which is 2x cubed minus cotangent x plus a constant. And this is a really important consideration. We do this a ton mathematically, that essentially what we are doing here is undoing the derivative operation. The integral is the opposite operation of the derivative. And that's a very, very consistent, teaching strategy in calculus. We typically teach you something, and then we teach you the technique to undo whatever operation we taught you previous. All right, so a bit of a longer one, and don't get me wrong, we could break this term by term by term, but I don't think there's a huge advantage to doing that when you have, a simple polynomial. I mean, simple in quotations maybe. I'm going to take that antiderivative then. So I'm going to write this as 2 over 4 x to the power of 4 minus 3 over 3 x cubed plus 7 over 2 x squared plus 2x plus a constant, and then we can use the notation. It's typically just a vertical bar at the end with the upper and the lower bound in place. And that's just to remind us that what I've written is the indefinite integral of the expression above, but we want to know the definite integral from 5 to 2. So my next step, and I'm going to do one thing before I do the next step, I'm just going to clean this up underneath it. I'll write it in red here, that I am going to use 1/2 x squared, x to the power of 4 minus x cubed plus, not much we can do there. I'm going to write a 7 over 2x squared plus 2x plus a constant. And so what I'm going to do is I'm going to evaluate that function at 5. So that's 1/2 times 5 to the power of 4 minus 5 cubed plus 7 over 2 times 5 squared plus 2 times 5, a bit of a mouthful for sure, plus a constant, then minus, and I'm going to evaluate the same function at 2. So this is going to be 1/2 times 2 to the power of 4 minus, the 5, sorry. That should be 2 cubed plus 7 over 2 times 2 squared plus 2 times 2, and then that constant creeps in there again. Just like our previous example, that constant will cancel. I'm not going to belabor this too much, but what I can say then is when I add all of those constants together, I get 267. Now, what that number is the area underneath this function from x equals 2 to x equals 5. I shouldn't say the underneath. I should see the area between the function and the x-axis of our polynomial from x equals 2 to x equals 5. Certainly this particular question, very, very checkable via the calculator. Remember that on your calculator, you don't put the antiderivative in, you put the expression inside the integral into your y1. All right, this looks brutal at first glance, right? This does not look like a simple function to work with. And I mean, it's not a simple function to work with. What we're gonna have to do is we are going to have to simplify it a little bit. And I just wanna rewrite the integral again because the photocopying got a little bit bad on me. So it's the integral from 4 to 1. Because my denominator is just t, I'm going to divide each term in the numerator by that. I'm going to do one thing to try to make this a little bit clearer. I'm going to write this as t squared plus t to the power of 1/2 minus 2 times t to the 0, just so we can talk about it, divided by t to the 1. So t squared divided by t to the 1 is t to the power of 1. T to the 1/2 divided by t to the 1 is t to the negative 1/2, and then subtracting by 2 times t to the negative 1. Now, you do have to be careful with this. A lot of students like to try to use that anti-power law, if we're going to talk about it, and they try to tell me that the integral of, and I'll just do t to the negative 1 here, dt, they try to do the power law. So they write it as 1 over, okay, my nu is going to be 0, then I'm going to have t to the power of 0. 1 divided by 0 is undefined, t to the power of 0 is 1. The derivative of undefined, well, it doesn't exist because it's undefined, so this technique fails. And I do, really want to stress that if you have the integral of t to the negative 1 dt, this is equal to the natural log of t plus a constant. And that is one that is on your formula sheet. It is just often overlooked by students. So we're going to apply our antiderivative term by term. The antiderivative of t is 1/2 t squared. The antiderivative of t to the negative 1/2 is positive 2t to the power of 1/2. Right? Think about that differentiation process. The 2 would get multiplied by 1/2, which would make it 1, and then that power would reduce by 1, and we would get back to t to the negative 1/2. And then I'm going to subtract 2 times the natural log of t. And then last but not least, I'm adding a constant, and to be consistent with the notation, I'm going to take that antiderivative and evaluate it from 4 to 1. So we are going to have 1/2 times 4 squared plus 2 times 4 to the power of 1/2 minus 2 times the natural log of 4 plus a constant. Then we're going to subtract that same function evaluated at 1, which is 1/2 times 1 squared plus 2 times 1 to the power of 1/2 minus 2 times the natural log of 1. Oops, almost forgot the constant there. My bracket's going to look a little weird, but that's okay. And now what I can do is evaluate this as much as possible. I don't want you to just jump to your calculator. It's important to build these algebra skills. 4 squared is 16. 16 divided by 2 is 8. 4 to the power of 1/2 is 2. 2 times 2 is 4. Can't do anything with 2 ln 4. We're going to leave it as is. I mean, you could write that as, the ln 16, but there's no advantage doing that. So we're going to leave it as is, plus a constant. Then I'm going to subtract 1/2. I'm going to subtract 2. I'm going to add 2 ln 1, and I'm going to subtract c. So just like in previous questions, we see that the c cancels. This is one that a lot of students, maybe they're not comfortable with logarithms. What's the logarithm of 1? The logarithm of any base of 1 is always equal to 0. Remember, that logarithm is trying to tell us what exponent do I put for its natural log. So what exponent do I put on e to get the value 1, and that exponent is always 0. So I'm just going to write underneath it that this is 2 times 0, and therefore we don't need to consider it. 2 times 0 is 0. So we have 8 plus 4 minus 2 minus 1/2 minus 2 ln 4. So 8 plus 4 is 12. 12 minus 2 is 10. 10 minus 1/2 is 9.5. And then we still need to subtract 2 ln 4. Let me get that 9.5 written a little bit better. Now, this is why we push that, don't use your calculator for everything, because when you use your calculator, it is never going to give you the exact value. It will take, 2 ln 4 and probably take it to, 8 decimal places, which isn't bad, but it's going to chug out a decimal value. We understand that completely, and so we will ask you to come up with the exact value to make sure that you can do the actual integration process. Okay, last one, and it's everybody's favorite, which is trigonometry, I'm sure. Right away, I'll show you what the antiderivative is. So we're going to take the antiderivative of this function, and what it becomes is we are going to have the antiderivative of 3 sine x is x, negative 3 cos theta, my bad. And then the antiderivative of secant squared is tan. This negative symbol still needs to be there. So we're going to be subtracting tan theta. And then to be consistent with my notation, I'm going to evaluate this from the upper bound pi over 3 to the lower bound pi over 4. Now, there's going to be a lot of trigonometry happening here. So what I'm going to do is I'm going to write those coordinates up top. The point pi over 3 on our unit circle, pi over 3 is 60 degrees. That means it has the smaller x value and the larger y value. And then the point at pi over 4 on the unit circle is our root 2 over 2 comma root 2 over 2. Now, the tan is going to be the gnarly one. And typically students don't struggle with the tan of pi over 4. I'm going to write both here. I'm going to write what the tan of pi over 3 is. The tan of pi over 3, remember, it's y over x. So that's root 3 over 2 divided by 1/2, which is to say root 3. And then I'll also write the tan of pi over 4, which is root 2 over 2 divided by root 2 over 2, which is, of course, 1, and positive 1. Important to say that, I think. All right, now we can do our antiderivative, or I guess evaluate our antiderivative. And what I'm going to have is negative 3 times the cos of pi over 3 minus the tan of pi over 3 plus a constant. It's bad of me to forget that. And I talked about how it should be there, and then I forgot it. I'm going to put plus c down there. That expression will be subtracted by negative 3 cos pi over 4 minus the tan of pi over 4 plus that constant. Again, very, very consistently, we see that this constant will cancel. I'm going to eliminate it right away. And then what I'm going to do is I'm going to use my points from the unit circle and evaluate this trigonometry. I'm going to keep the square brackets for now. So this is going to be negative 3 times 1/2. That's the x coordinate at the point pi over 3 on the unit circle, minus the tan of pi over 3, which is root 3, minus negative 3 times the cos of pi over 4, which is root 2 over 2, minus the tan of pi over 4, which is 1. And now I can clean up that expression. This expression, is going to be negative 3 over 2 minus root 3 plus 3 root 2 over 2 plus 1. And then all we can do here to try to clean this up is get everything with a common denominator and deal with it that way. This is going to get a little ugly, but all those terms that aren't fractions, I'm going to multiply it by 2 over 2. So I get negative 3 over 2 minus 2 root 3 over 2 plus 3 root 2 over 2 plus 2 over 2. Well, negative 3 over 2 plus 2 over 2 is negative 1 over 2. So I'm going to have negative 1 minus 2 root 3 plus 3 root 2, all divisible by 2. And this, although it doesn't have to be in that order, maybe I'll write it beside it. This is what I have in my key. It's the same thing. But typically we put that positive number first. So 3 root 2 minus 1 minus 2 root 3, all divided by 2. This is a little bit of an ugly one, just getting that, typically we like to see radicals combined, but they don't, because they don't have the same radicand. So that, again, is the exact form answer, whereas using your calculator is going to give you that as a decimal, which is approximate. And that has value. Depending on what you're doing this for, approximate may be good enough, but we are going to expect that you can get the exact value answers as well. All right, so the assignment is here. Definite integrals are very similar to what we did in chapter 10. It takes practice. Try to remember, chapter 3 when we were learning the derivative. Derivatives didn't become, and maybe they never got easy, but they didn't become, routine until you had done a few dozen questions. And that's just as important when it comes to antiderivatives. So make sure you're chipping away. And if you struggle, as always, email, please.